Okay. Yes, that now works. Okay, so I'm also part of the NEST team, led by Jack, and I'm kind of going to focus today on space weather of the extrasolar kind, focusing on the interaction of stars near to the solar system and the activity of those stars and its impact on potentially orbiting habitable extrasolar planets. And really I'm focusing on a path towards how we might try and do the science from the moon and why it's really essential to eventually go to the lunar far side. Okay, just for context, I'm going to just show a picture of a recent event from a few days ago where there was an M-class solar flare, a quite long duration one associated with the coronal mass ejection. That coronal mass ejection eventually actually interacted with the Earth's magnetosphere, giving us the G2 geomagnetic storm, which is quite mild. Gave us some nice aurora if you were down in New Zealand. This, of course, was a very mild event. There can be much larger events. For example, if the Carrington event of 1859 occurred today, that would have a very significant impact potentially on the power infrastructure in the US, with some cost estimates of about $1 trillion potentially damage being done. So they are very significant events, and of course they play a very important role. They have to be very carefully monitored and understood in the context of sending astronauts to the moon and Mars. But on geological timescales, they're also very important, geological and cosmological timescales, because they play a very important role in impacting how the atmosphere of the planets evolve. The very good example is the recently established relationship between coronal mass ejections from the Sun and the evolution of Mars' atmosphere. Essentially, Mars lost its atmosphere early on in the solar system's development due to the heightened CME activity of the Sun. Ion pickup eventually leads to loss of the atmosphere and may have been the main reason why Mars is no longer a habitable planet. Broadening beyond just Mars, of course, Venus does have a very dense atmosphere, but it's thought that it may have lost a lot of the water content in that atmosphere by a very similar process. We're lucky in the case of the Earth that hasn't happened. We know that magnetic activity of stars can impact habitability. It's not clear, one very important characteristic of the Earth is that it has a reasonably strong magnetic field that may play a role in shielding it. That relationship is not very well understood yet, but understanding activity of the star and trying to detect magnetic fields of planets is very important in terms of the context of habitability. Now, moving beyond our own solar system, you often hear the Sun referred to as an average star. It's actually quite a large star. Most stars are much smaller. They're M dwarfs. For every G dwarf we have, there are 20 M dwarfs. So M dwarfs have become a very hot topic now in the search for habitable exoplanets because most planets that are evolved are M dwarfs, and statistics from Kepler have shown that rocky planets are very frequent around M dwarfs. In fact, statistical analysis suggests the nearest habitable planet orbits an M dwarf within about 3 parsecs. And that's a huge focus now for future missions to try and detect biosignature gases on nearby exoplanets. M dwarfs are really the future. However, there are some issues in the context of activity. I'll just mention 2 very obvious examples in the last year or so of very exciting M dwarf systems that are hosting potentially habitable planets. This includes the very cool M8 M dwarf TRAPPIST-1, which has a whole zoo of planets, some of which are within the expected habitable zone of that planet. And of course, our nearest star, Proxima, has a likely rocky planet companion that may be in the habitable zone. So this, in the last year, this strong focus on M dwarfs has really been manifest. However, there are some issues in the context of the activity of the star. This is a plot which shows the position of the habitable zone as a function of stellar temperature. So for a G dwarf like our Sun, as you might expect, the habitable zone is about 1 AU away. So we have Earth in the habitable zone, Mars on the edge. As you get cooler and cooler, that comes closer and closer. So any kind of activity from the star is much more impactful. It's actually the square of the ratio of the difference of the distance more impactful on that atmosphere of that planet. The example of TRAPPIST-1, for example, these planets are orbiting at a very, very small distance, much closer than Mercury orbits the Sun. Another issue is the activity lifespan of a star. Our Sun is very active as a young star, but its activity rapidly decreased because that activity was powered by rotation. And when the Sun was very, very active, it was rotating very fast, but it had very, very large X-ray luminosity and a very large solar wind, and that allowed it to lose angular momentum, slow down, and become more benign, middle-aged, well-behaved star. Unfortunately, M dwarfs remain petulant for much longer periods of time. Here I'm showing just the activity lifetime as a function of subclass within the M dwarf spectral type regime. We see, for example, this is the Proxima Centauri spectral type, about M5, M6, and we see it remains active for many gigayear. And Proxima is actually quite an old star, but it still is a star that flares very frequently. So not only do you have much higher exposure to that activity, it lasts for much longer. And the question we want to address in summary is, how important is that activity in governing the habitability of planets orbiting M dwarfs? And how important is it to have magnetic fields in order to shield a planet from that activity? And is that a very important role in establishing whether or not a planet can host a biosphere? We want to try and address that question via low-frequency radio emission, because you can actually trace both coronal mass ejections, as was discussed in Bob's talk, and the presence of magnetic fields via low-frequency radio emission. I won't spend long on this slide because I think Bob's covered it very well. A very nice signature you see when you have a coronal mass ejection very often is the presence of a type 2 radio burst, particularly at low frequencies. Most of the emission is at low frequencies, and as Bob showed, if you want to trace that out into the interplanetary medium, you have to go to frequencies below about 10 megahertz, i.e. space-based. Of course, it's a very highly variable emission. The brightest burst we've ever detected is in 1947 from a very famous sunspot group, the largest ever detected, which was the brightest ever extraterrestrial radio event. It was, for those of you that speak radio units, 10 to the 11 Jansky. That's very bright, but very rare. Jack's face tells me he knows that's a big number. Okay, what about planetary radio emission? It turns out all the planets that have magnetic fields are also very bright radio sources, including Earth. However, the radio emission in this case is produced at a frequency corresponding to the magnetic field strength of the planet. What does that mean? So here I'm showing the radio power of the planets as a function of frequency. It means this is a cutoff. This here is the cutoff that is limited. So you can't have any emission from the ground detected below the frequency cutoff of the ionosphere. It gets reflected back out into space. That means that only Jupiter's radio emission can be detected from the ground. In fact, a single dipole will easily detect a burst from Jupiter. It's so luminous. However, if you want to detect the Earth or Saturn or any other of the planets that have magnetic fields, you have to go to space, even though it's extremely luminous. And that's very important in the context of why we want to go eventually to the far side of the moon. Can we detect similar radio emission from planets? We hope so, and it's very important because it's our only method we currently know of to measure and determine whether or not planets, extrasolar planets, have magnetic fields. We can measure rotation rate. We can provide insight on internal structure. If they've got magnetic fields, that means they must have convective interiors. Like I mentioned already, space-based observations will be crucial, particularly from the lunar far side. All right, how many planets have been found thus far? After decades of searching, there have been no detections, and there are many reasons, I think, why that's been the case. The biggest problem, I think, is that all these telescopes have a very small field of view, which means they point at some planet and observe for a few hours to try and establish whether or not there's any radio emission. However, the radio emission from planets is very variable. Here is the radio power from the Earth as a function of input solar wind speed. If you vary the solar wind speed by a factor of a few, you can vary the radio power from the Earth by a factor of 1,000. What happens, when do you typically have the Earth in this regime? When you have a geomagnetic storm. So if you really want to be able to detect radio emission from planets, you've got to monitor them, the same way we monitor the sun for radio emission. So we need to have the capability to monitor planets all the time. That's a very large focus for my group from the ground. We have built an array that's a pathfinder for what we hope to eventually do from the lunar far side. It's an array of 288 antennas spanning a few kilometers. I'm just showing you the inner core via drone shot with some grad students for scale. And you can see lots of antennas with lots of cables underground. It's a very large project that's been motivated by this search for radio emission from exoplanets. This is about the inner 10% of the array. And we use that array to be able to produce images of the entire sky every 10 seconds. This is a movie of the radio sky above the array those things that are flying overhead are airplanes that are reflecting interference. And what we do is that we try and identify important stars. So here, for example, are 3 known stars that flare very regularly. But what we really want to do is find every single star of interest in the sky and measure the radio emission from that location. So you're going to see in a second the red dots. The full sample will be in another couple of seconds. They're all the M dwarfs within about 25 parsecs. We measure the radio power continuously. The upcoming yellow dots are all the FGK, more solar-like stars. And we now have light curves for every one of those stellar systems continuously. But what we really wanted to focus on here, of course, is the plans for the future from the lunar far side. Because if you want to actually study terrestrial planets, you have to go to space. If you want to be shielded from the Earth's radio emissions, you have to go to the lunar far side. So I'm working with the NEST team to try and establish requirements for this lunar-based array that can do solar science, of course, cosmology, but also try and measure radio emission from planets. And there's a lot of parameters we try to tweak. We want to define a strategy. Of course, as I mentioned, you want to be able to monitor stellar systems continuously. Our plan is initially put beams on the Alpha Cen system, which is obviously AB in Proxima, and monitor that stellar system continuously. As we grow capability, we'll add beams on other nearby important systems, particularly those that are known to have nearby exo-Earths. Here is just a plot showing our sensitivity. This is a plot which shows all the radio emissions from the sun, and here is a plot showing the luminosity of the brightest bursts. Moving that emission to Proxima, or to Alpha Centauri, for example, we can detect that from the lunar far side with about 100 dipoles pretty easily, and get the first characterization of coronal mass ejections for that system. What about planets? There have been lots of studies trying to predict how bright the radio emission would be from planets. It's not very well understood because there are a lot of scaling laws you have to apply. But here's an example from a paper from a few weeks ago from Blakely Burkhardt and Avi Loeb, looking exactly at the case of Proxima. And here's their prediction for the frequency and strength of the emission from Proxima. Now, we would need about 10,000 lunar-based dipoles for a detection. However, if the radio emission is as variable as the Earth's radio emission, that could get 1,000 times brighter. And so once again, we may be able to find it with 100 dipoles as long as we monitor. This becomes very important in the future in the context of missions that are going to try to characterize planetary atmospheres. Here's an example of what we expect for JWST, but of course in the future, LUVOIR and HABEX. If we have a lunar array monitoring these planets simultaneously, we will know which ones have magnetic fields and are the primary targets. And we can also try to interpret what we see based on what the space environment for those planets might be. And I'll stop there and take questions. Thank you.
Well, if there are no questions, let me ask, how do you separate the multiple stars in Proxima?
Right, so that's a resolution question. You will have problems with Alpha Cen A and B, but I think separating Alpha Cen A and B from Proxima will be easy enough. They're a couple of degrees apart. So it just involves making sure you've got beams on each. We expect very different behavior from Alpha Cen A and B compared to Proxima. M dwarfs have very different magnetospheres, very different coronal conditions. We don't really know what we're going to see there. But I really hope in the case of Alpha Cen A and B, we might be able to see solar-like behavior, like type 2 bursts. One very good way to try and separate them, however, is to have a small telescope observing the optical from the ground. And you probably will see a large flare coming from the star that has that has a radio burst, and that'll be a useful way.
Would it be worth having a dedicated radio monitoring of the Proxima Centauri system on the ground to start to get some baseline on what that variability might look like?
Yeah, that's kind of what our program is to try to do all the. We'll be doing all 4,000 stars, 25 parsecs. I think the likelihood of getting Proxima Cen B, however, is very low until we get to that lunar far side because the frequency is just likely to be too low. So I think we'll make a lot of progress with this new array from the ground, but it's really a pathfinder, I think, for what we'll be able to do from space. One eventual very cool thing might be that when you actually have a geomagnetic storm on a planet, the atmosphere changes. Normally, if you want to characterize biosignature gases on Proxima Cen B, you're looking for O2 and O3 absorption spectra. If you have an aurora, suddenly the atmosphere goes into emission, and you have a very bright oxygen line. So if we're monitoring from the lunar far side, Proxima Cen-b, and we suddenly see an auroral radio signature, we can trigger HAB-X or LUVOIR and say, now is a great time to try and actually measure the oxygen in that atmosphere. So there could be a lot of interplay there with future missions.
I think you may have covered this issue, but I can't seem to understand how you can get enough signal-to-noise ratio from a signal that would emanate from the exoplanet vis-a-vis what would emanate from the star itself. The ability to differentiate between what comes from the magnetosphere of a exoplanet relative to what comes from the star. That's my question. How do you differentiate that?
So in terms of luminosity, I don't think that'll be an issue. For example, Jupiter very often outshines the sun at radio frequencies. When Jupiter has a bright radio burst, it's typically brighter than the sun by a substantial margin. So I don't think luminosity is an issue. Now, in terms of the properties of the emission and how you can distinguish them, I think the emission we expect from the star during a type 2-like event has a very characteristic time-frequency behavior. The behavior of the planet, by comparison, is very different. It'll be very highly circularly polarized emission that actually repeats periodically with the rotation of the planet. I think in an ideal scenario, what we'll see is a bright radio burst from the star that looks like a characteristic type 2 sweep, and then hopefully 18 hours later or 10 hours later, suddenly up will pop the planet as a periodically pulsing source. That would be the ideal scenario. It may be more complicated than that because of the issues you're mentioning.
Okay, let's get the speakers up. And let's get the speakers up here for a panel discussion.